Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is kind of a strange talk for me to give. 2 years ago, I've done a lot of things at Microsoft. I've been here a long time. And 2 years ago, I got asked to join the quantum computing effort. And I thought that in itself was kind of strange because I'm not a researcher. I'm not a physicist. I'm not a mathematician. I ship products. I built a lot of stuff, and I write code. I'm an architect, and wasn't quite sure what I would do, so I started looking around. And the first thing I look for are tools. I build tools. I try to make people more productive. And I started looking around this whole field at what tools were available. And the answer was none. There was basically nothing out there. Everybody would write what they needed for their thesis, get it done, ship it, and throw it away. So I started building a platform, and then I went around talking to all the top names in the field. What would they do with a quantum computer if they actually had one? And I gave them some sizes, gave them some reasonable technology, and they all had things they would do, some pretty surprising, but none of them had an idea of how they would do it. So they knew they had problems to solve, but no one really had ways of doing it. So this talk is about trying to fill some of that void. It's a tool that we've built that is evolving, that we've done some things further than anyone else has ever done in the field. I've thrown back some slides that haven't used for the rest of this trip because this is the first computer science-based group I've talked to. They've all been mathematicians and experimental physicists and theoretical physicists, and I get to put some comp sci back in. So hopefully some of those slides will be interesting to the audience. But LIQUi is designed so that we can create a simulation environment to make it easy to do really complicated quantum circuits. And you'll see how complicated in a little bit. Efficiency is a real problem. If I could do quantum simulation easily, I wouldn't need a quantum computer. So how big can you go? What can you do on conventional hardware, and how efficient can you be? And actually, those are the slides I threw back in to give an idea of how hard that is. Circuits have to be retargetable for many purposes. What I did is started in the middle, pretty much how you would for conventional computer science. I started with an abstract idea of what a quantum computer is, logic, gates, that level, and then worked my way up into circuits, into, if you will, assembly code equivalents, going up, and finally we hit a language at the top that you can actually express in and compile down into that abstract model. We did that first. Now we're going the other way from the abstract model down into target hardware. So noise, what things fall apart, communications limitations, only certain things can talk to certain things. How do you compile down into that? How do you optimize for actual experiments you're going to do in the lab and machines you're going to build? It turns out there's different ways you can attack this because, again, you can't do it all on a conventional machine. You can pick specific things you're good at. You can be good at noise. You can be good at physical modeling. You can be good at circuit modeling. So we've built different simulators that all plug into the same environment. So you can write it once and then run to different simulations and trade things off. And then flexibility. I'm an architect. I like platforms. So how do you make it so you can plug in your own modules, change the definitions, extend this over time? I don't like things that I write and then get thrown away 6 months later. So let's talk about the platform itself.
So
yes?
You're simulating a quantum computer. How far away, of course we'd like to build the quantum computer, how far away is the real computer from the one, in time, from the one that
we're going to talk a little bit about one we can buy today. Okay, so we're not that far away in terms of what people will tell you is a quantum computer. And the question, is a paper that just came out that we just did. But realistically, to a real universal quantum computer, minimum 10, probably closer to 20 years. That's about the time frame we're talking about. Now, pieces already exist. Experiments exist. Demonstrations exist. But the real thing that, let's say, I put up in the cloud and you're going to connect with Azure and use it as a service and run big simulations on, 10 years minimum.
Okay, and your goal here is that by the time it arrives, we want to be ready to program it.
Well, plus I need to program it. So I'd use this as the front end to program it. That's why there's the back end. Right, so by the time you get used to running the simulation, you could also instead target the real machine. So we're going to start with the language. I spoke to Don last night. He said, you've got to push F#. Got to push F#. Don always says, I've got to push. So I've got my F# mug here. I'm one of the few people he has to tell that to. I've been using it since before it was version 1. Everything I've written in the last many years has been in F#. And I'm a functional programmer from way, way back. So preaching to the choir here. But I'll show you why it's good, why it works well. This is also why it's language-embedded quantum operations. Think LINQ. This is a monad that's been implemented inside of the language, and we've extended the language in some nice ways. But again, it's a .NET language, so you can come, well, for F#, you can come from scripting level. In fact, you don't have to compile anything. The whole thing can be run from scripts, which means we can put this as a service. You can just submit the script. You can come from C# or any other language that can link with the library. So the whole thing is contained in a library. You can get to it from any language you like. It's just, for me, the most natural and basically designed for F# as the top level. Everything compiles into gates. When you see gates, think function. So everything has a definition. A logical gate is just, a function that implements an AND or an or specific quantum gates that we're going to talk about. Once this all gets compiled, it gets sent to simulators. We have 3 simulators currently. The first is a universal simulator. This will do anything any quantum computer we might build will do. But it comes at a price. You can only do, on a typical 32 gigabyte laptop, about 30 qubits. It's 2 to the 30th to complex numbers to store a state. And then you have to operate on that. So you do the math. You actually do pretty well fitting it into 32 gigabytes. You want another qubit? Double the memory. You want another qubit? Double the memory. So I have a simulation running right now. This is going for 16 days. That's running on a 96 gigabyte machine, and that's nowhere near big enough. We actually have a bunch of machines ordered that are a terabyte to do a lot of the problems we want to do. But there's another way to go. Don't make it universal. Get rid of a lot of the gates that make it that complex to simulate. And there's a version of the simulator that uses only Clifford group operations. Don't have to worry what that is, but they're called stabilizers. The interesting part is every quantum error correction code only uses stabilizers. So you can do research into very sophisticated quantum error correction. We'll talk about that a little later. But I can do tens of thousands of qubits as soon as I don't make it universal. So this is where you can trade off the number of qubits versus the operations you're allowed. And then there's a Hamiltonian simulator. This lets you do actual physics. And it turns out a lot of the types of machines we're talking about depend very much on the actual physics. You can't just abstract it away. And there are times you don't want to. There are problems you'd like to set up, especially in machine learning, that require the actual Hamiltonians. Again, this is universal. Again, takes about 30 qubits in 32 gigabytes, but it's slow. So now you've traded off from the universal to make it more physically accurate. Now you have to run much slower because you have to fix up all the problems of basically doing a differential equation that you're solving along the way.
What does Hamiltonian buy you over universal?
It buys you physical modeling. So for instance, I can actually do time derivatives. I can actually watch. There are times I actually, say, spin glass problems. We can do some of these where I actually have to be flipping. I'm doing annealing. And to do annealing, I have to be able to drop a temperature. And to drop the temperature, I have to actually do, not each gate, but between each, the interactions between all the gates over time as we go from gate to gate.
So it might give you a more close physical simulation of the machine, which I suppose
Yes.
might be, but that doesn't change the output. It's going to
no, it does.
either way.
No. If I'm doing annealing, right? When you do annealing, do simulated annealing on a regular classical machine, you have to break it up to do time simulation, right? You're actually going to, that's what the Hamiltonian will do, as opposed to saying if I just went from here to A to B, I lose all the dynamics in between. I won't get the right answer.
So it is not like the difference between a logic simulator for a CPU and
Right.
something that is doing the voltage levels.
It is actually a different problem in coding completely.
Oh, why?
Right, and so we actually have different ways of looking at the problem, and LIQUid will let you write it once and then send it to different ones and see how they operate and how they work.
So question, what is
Yep.
the resolution of the Hamiltonian?
Whatever you'd like to define. If you know the physics, you're doing a trotterization, and you get to pick the trotter number. So if you want 1,024 steps between each, and you want to do The problem is, I don't want to go too far down this track, and we can do it offline, but the problem is the terms that are in this equation aren't commutative. And you don't know what order you actually have to compute them in, because they really want to all be done in parallel. So what you have to do is find enough time steps to get rid of the anti-commutivity problems, and that's the trotterization. So by picking a finer and finer trotterization, you get a more accurate answer, but each one is twice as slow. Every time you add a trotter number, it's twice as slow. So everything in this game is exponential, and you have to trade off very carefully, because things can take literally forever. Runtime. So we have 3 runtimes currently. The client runtime. This will run on your laptop, your desktop. You just bring it up, put in the script, or write the code. It works. Service. It's a virus on purpose. You sit there here in the lab and you say, I have accounts on all those machines on my LAN. It'll self-install itself across all of them. It'll become a Windows service. They'll all hook up and talk to each other. And now you can run ensemble simulations across all the machines in the lab and then have them take themselves down and deinstall, and nobody knows you were there. There's nothing to tune other than an XML file that says, here are the machines I have accounts on, and here's where to run the executable from. Everything else is automatic. And since we can do that, we can go to the cloud. You have a cluster, you want to run on Azure. Here you submit a script. It goes off, sends the script across to, 5,000 machines, does your ensemble, brings it back. I'm using the word ensemble because you don't ever break up a computation across machines. You'll see why in a few minutes. It's just too inefficient. There's no way you can afford it. But most of these are statistical computations. So you want to run thousands of them anyway. So you might as well put 1 per machine and then use all the threads available on those machines. But nice thing about Fsharp, it's introspective. We have reflection. So we go down through all these functions. Instead of running them, we have them describe themselves back. We build the AST, we read the AST, and we actually create a data structure, which is now the circuit that is represented by all those functions. Once we have a data structure, we can do anything we want to it. We can optimize it and then send it back down through the simulators again. We can do quantum error correction. We can apply, just like you would do in the classical case, replace each one of these gates with an error-corrected version that runs on multiple bits, or in this case, qubits at the same time, does voting, does correction, fixes things up based on error models. We'll do some examples. Solovey-Kitaev. Most of your computations are rotations. They're things you want to move. And the problem is physical hardware can only let you usually move in certain discrete rotations. This lets you build equivalent circuits that gets you to any exact rotation you want by doing these coarse ones along the way. And so this will say, I need a 10 to the minus 6th accuracy angle, and this will put the 1,000 gates together necessary and replace that one angle with the gates you actually have on the physical machine. So this is going down now from the abstract level, saying here are the gates I actually have, replace them all as needed. Noise. Noise is a big problem. We'll talk about that in a little bit. But if you look at something quantum, it falls apart. Looking at it doesn't mean you looking at it. It means the environment interacting with it. Things decohere no matter what you do. And so you have to be able to handle that noise as the quantum error correction, but you also have to be able to model it. The simulation won't do you much good unless you know what's happening. So there are different types of noise. Bit flips, phase flips, just bleeding of energy off to the environment as things slowly decohere over time. All of that's modeled in the system, and you can apply that to all of your circuits. We'll show you what that looks like.
Do you
Yeah.
have examples of this? At the moment,
Oh,
I'm
yeah.
completely lost because I just don't have enough background.
Oh, I'm going to be doing details on each. This is just to show the architecture.
Can we get to the... Yeah.
Okay, let's get there. Okay, so I'm going to just quickly finish this export. Just let you take these data circuits and send them to backends. We have 2 types, classical. We have people who have giant supercomputers and want to be able to run this, so we give them in a form they can do linear algebra and say, go run. And then quantum, as I mentioned, you have a lab experiment. You actually want to output to control that lab experiment. And finally, rendering. Everybody hates drawing all these circuits for technical journals. This draws them for you, and you'll see examples. Okay, let's actually get into things. I'm going to skip the bit of Fsharp syntax. I'm going to assume most people in the room have an idea. But, parens are for association, arrays, lists, how you call things. You can pipe, what null looks like. And then we've added some operators. So we've overloaded all the usual math operators to do complex arithmetic. nothing you wouldn't expect. We have Kronecker products. We have vector matrix multiplies. All of these are full precision complex operators. There are convenience operators that let you, for instance, map one gate to a bunch of qubits. Say, do this gate on all these qubits. Just things that make your life easier. There's just some nice things that say, no matter what I have, it's a bag of stuff. Look in there for qubits, turn it into a legal list of qubits to use. So again, convenience functions. When I talk gates, this is what I'm talking about. So these are our bottom level logical operations that we've been talking. So an X, which is a flip in one dimension. So we're in 3 dimensions here. We can flip in X, flip in Y, flip in Z. So these are just saying flip the state. It's a vector on a sphere, and we're flipping wherever it's pointing in the X direction, the Y direction, or the Z.
So I should think of the input to the gate as a unit length 3 vector.
It is. Well, it's a unit. It's always unit, and so it's only 2 angles basically, right, where it sits. And so there's 2 complex numbers, and what they actually are pointing at is the north pole is 0, the south pole is 1. That's the basis here. And you're just giving the magnitude in each direction in between those 2 complex, which gives you the phase as well. And that's how everything in the entire system looks, is this collection of complex numbers that describe a state where all the qubits are pointing in this 0-1 sphere, in effect. It actually gets more complicated as soon as you have 2 of them. You can't actually visualize it, but one that works. But the matrix is what you have to do. That's what you multiply your 2 complex numbers by, if it's a 1-qubit gate, to get the output of applying that gate. So one of them flips it in one direction, one of them flips it along the imaginary axis, one flips it along in the other case, the Z axis. The Z is the north pole and south pole. So 0 is this way and 1 is that way. Everything, including Z down, Z, S, T, R4, are examples of rotations that are going half an angle further each time. So Z, we're flipping the whole way. S, we're moving half. T, 1/4, 1/8, and you can do as many as you want, but just showing that's what the rotations. They're just the bottom corner going higher and higher, or smaller and smaller in terms of the value. Identity, why do you need identity? You multiply, you get the same thing out for noise. Things that just sit there go bad over time. So you want to be able to insert identities and watch them going bad. Hadamard is what gives you superposition. If I put in somebody who is pointing at the North Pole, his value is 0, and I run him through a Hadamard, I get somebody who's half pointing at 0, half pointing at 1. He's in superposition. So the difference here is, think of it as a probabilistic bit. You can have it anywhere between 0 and 1 with a probability. The reason it's more than just that, it also has a phase. So you can point to anywhere on the sphere where straight up would be 0, straight down would be 1.
So they're not just 3 vectors, but probability distribution.
They are.
Vectors.
Yes. Okay. And in effect, they're actually in all of that. It's when you try to look at it, you get a probability of seeing the 0 or seeing the 1. They become probability when you look at them. They're actually wave functions, if you want to be exact. The equivalent of, in classical computing, you have a NAND gate and build everything out of NAND gates. Here you have a C-NOT. It's a controlled NOT. If the top is a 0, the bottom goes through unchanged. If the top is a 1, the bottom gets flipped. And that's the controlled NOT. But remember, it's some probability in some direction. It's a combination of 0, 1, and that passes through, and you get a combination of the controlled NOT out the other end. Swap flips the values. Measure is how you get actual conventional data out. You put a qubit in, you measure it, and with those probabilities, you're either going to only get a 0 or a 1 out. You get a bit. And that's how you collapse everything down to a bit. You could, of course, use a bit to say whether or not to do a gate. So you'll see, when you see the double bar, that means it's a bit. So there's a bit on top of that X that says, if it's a 1, do the X. If it's a 0, don't do the X. And then finally, I want to create a qubit. I put in a binary value, in this case the 0, and I get a qubit back out the other end. So this is pretty much what the zoo at the bottom looks like. I just want to give a feel for what you're going to see on other diagrams. All of these are unitary operators except for the last 3. Unitary means when I pass them through in one direction, I can play them back in the other direction, and I get the same thing I started with. So every quantum circuit you see outside of when we measure is playable all the way from the beginning to the end, and from the end all the way back to the beginning, always. And there are a number of things that does for you. In the actual physical side, there's no heat dissipation. It actually takes no energy to do this. You're running superconductive, and everything stays in a superposition. But what it also means, if I had an AND gate, can't actually do an AND gate because you lose information when you go through the AND. So you have to do two wires. One is actually the AND, and the other is the information to put it back if you go the other way. And that's why all of these look like this with the matrices, because you can run them in either direction. OK. Hello world is what we would do for the canonical example for conventional. Let's do the canonical hello world for quantum, which is called teleport. Alice entangles 2 qubits. So we have 2 qubits on the left starting in 0. We're going to superimpose the 1 qubit so he's between 0 and 1. The controlled knot entangles them together. So this is called an EPR gate or an EPR circuit. Einstein-Podolsky-Rosen. I always get it wrong. But all it means, we have 2 qubits that are maximally entangled at this point. They completely share mutual information. Somebody wants offline, I can explain all the math and how it all goes together. But Bob is going to take one of the qubits to the other side of the universe. Okay, Bob walks away with this guy. Alice is given a qubit with a message on it. It's somewhere on that sphere we talked about, a vector pointing somewhere. She entangles it with the qubit she still has. And then she's going to measure both qubits. Now, what I should mention is as soon as she entangled it, Bob's qubit changed, no matter where he is in the universe. And he actually has the answer, but it turns out he can't see it. The answer is encoded in a way there's no way. So it looks like we broke relativity, that we can go faster than the speed of light and take this thing from one end of the universe and send it to the other. But the information hasn't been transferred yet. The state of the qubit changed, but you can't do anything with it until she actually reads out the state of her 2 qubits, transmits them by a classical channel, which means now she's got to send these 2 bits across the universe. We're back to the speed of light. And then Bob can use it to decode the qubit. Those 2 bits are enough to get back an infinitely accurate representation of what was put in. So he was able to transfer a lot of information, but he still needed those 2 bits to get it back out. Don't worry about what it all means. What I'm trying to show is the way these circuits work is they look like a staff of music. Each one is a qubit. You apply gates on or between them along the way, and everything moves left to right. This is how you draw circuits. This is how the gates look in them. And this is, believe it or not, about the simplest example you can do. Bob recovers the sent message, and everybody's happy. Let's actually look at the Fsharp code. Okay? Again, I'm not going into detail. This isn't a course on quantum computing. I'm trying to just give a feel for what this looks like when you play with it. I should also mention I didn't draw this circuit. When you write the code, the circuit comes out automatically. So everything gets rendered for you as you go. So that EPR circuit is just an Fsharp function. It takes a list of qubits, affords a Hadamard on the first element in the list, and a controlled knot on the first 2 elements of the list. So you can hand in variable lists, and all the gates operate on however many qubits they need from the top of the list. The rest of the algorithm teleports a function. I'm going to name the first 3 qubits in the list. I'm going to do an EPR function on Q1 and Q2, C naught the first 2, and Hadamard, measure it, binary control it, measure it, binary control it, and there's the circuit. So it's not a lot of code. You can very quickly build these up. And of course, each one of these you build is a gate or is a function. And so you can build them all the way up as deep as you like. And there's also some pseudo gates, so I can put little labels like the source and the 0 and the destination on there. I can do some simple optimization. Fold says move everybody to the left. That doesn't hit someone else. This is things you could do in parallel in a machine. And now everything lines up nicely, looks prettier. And if you're doing a journal article, instead of saying giving me SVG code in HTML, you can say, nah, give me Latex source. And so this is QCircuit output in Latex. So every paper we've been publishing, it's just auto-generated by the simulator, all the circuits we do. Now, this is the slides I threw back in for this audience, just to show you what it takes to do this on the computer science side. So we have these gates. The gate is a unitary operator that's 2 to the n by 2 to the n. And so if you have n qubits, that's 2 to the 30th by 2 to the 30th. It's big. The state vector, keeping track of all of these qubits, is also 2 to the 30th in size. You multiply each of these gates by that. So if you do this, it's extremely inefficient, takes ridiculous amounts of memory. It's not pretty. You run out of simulation address quickly. You run out of memory quickly. I mean, everything just goes bad. The state itself only gets that big when qubits are entangled, like we showed in the teleport example. So if things are in registers, if they're separate from each other, you really don't need that big a vector. You only have to keep the things that are entangled together. Other things that are separated are very small. When you start out with 30 qubits, it only takes 30 memory elements. If you entangle 2 of them, those 2 just became 4. You entangle that with another 2, that becomes 16. And so if you keep track of the entanglement, you can be very efficient about the size. But you can't compress it further. It's dense at that point. There's nothing else you can do with it. The operator is really sparse. You may just have these, yeah?
So there's a huge amount of similarity between sort of quantum programming language and probabilistic programming language.
Mm-hmm.
And when we're doing inference in machine learning context in very large state spaces,
mm-hmm.
we almost never try and actually represent every possible state.
Exactly.
And I guess certainly if there are known independencies between the
mm-hmm.
variables of qubits, then we would factor those away and reduce the state size.
Mm-hmm.
But then I guess people often use approximations that can be extremely accurate.
Can't do it here. And the problem is it's not probabilistic. It's fully deterministic until you measure it. And those effects can be extremely fine-grained. You don't know to the end what you can approximate. There is nothing you can approximate. Is where you fall apart here. I mean, I did large-scale, machine learning for years, and that was great. Now, I could take massive problems, the size of the web, right, and bring them down. And here, you don't have the luxury. You actually have to keep every, full precision complex number all the way to the end. And then you can actually measure it out probabilistically and throw things away. But you don't know until the end because you're actually keeping all of the fine-grained interactions. You don't know which ones are important. And so it's frustrating as hell. But if you really want to simulate what goes on in the machine, you can't throw it away. That's sort of the bottom line. We can talk about it if you like, okay? Yeah. So the problem is you have a really sparse operator, but again, it's massive and it's hard to keep track of. And remember, even if I've got a little gate, I have to expand it out to the size of the state vector to multiply the two. So I have, even for little gates, I have the same problem. So back to the standard talk, this is just Fsharp code. So we put it in a classical wrapper. You call the function just like any other classical function in here. Every top initial one is a random state vector we started with. Simon's question, there's your magnitudes, the complex number on 0, the complex number on 1, saying where that vector is in the sphere. We go through, we read out the bits that says whether to do the x or the z flip, and lo and behold, we get the same vectors back out. Hello world works. This is the equivalent of you run it through, it comes out, you get in hello world, everything worked. Your simulator actually does something useful. This can also be run as a script. So you've got multiple options. You can just run FSI directly on the script and say, do it. You can do a use, which lets you stay in the simulator after it runs. You can look at the states and the values and all of that. You can have LIQUi run it for you, which will take the script, compile it into a DLL, and then reload the DLL back in. Of course, now you have a DLL, so you can also run the DLL directly. So you've got lots of options from a script level if you don't want to actually get into a Visual Studio environment. I said I wanted to make this fully extensible. Here's the actual controlled NOT gate. This is all the code for it. Everything that's in here can be rewritten by the user, can be extended, can be replaced. And so you have a name for it, some help. You have a sparse matrix definition that says here are those elements in the matrix I showed you on the earlier slide. And drawing is the LaTeX commands for QCircuit, parameterized, so you can say, put this on this qubit, put this here, here's how I want it drawn. And that's it. So that's all you need to do a gate. I also said you could take those same functions and turn them into circuits. This is how you do it, into a data structure. You get a circuit compile of the teleport function, give it some qubits. If I say dump the data structure back out, you get back out a definition of all the different gates that were in teleport, what matrices, what wires they're on. And then from this, you can go to anything you like. You can go to a supercomputer. You can go to actual control of a system. Just want to show you how compact this can be. This is an entanglement test that says superimpose one qubit and then entangle it with everybody, and then measure them all. Well, since everybody's fully entangled, if I look at one of them, they're all going to collapse to the same thing. So if you look, we get, with about 50% probability, sometimes we'll get zeros, sometimes we'll get ones. No matter which one you looked at first, all the others collapse to the same thing. To generate that circuit, we created a function that just said, Hadamard the first qubit, remember him, map to the tail a C0 between him and everyone else, and then map a measurement across all the qubits. So you get very complex very quickly with very small amount of code. Parallel version, this is a little more complicated version. Then I said fold it. And now everybody moves in time. The 48 time steps really only takes 10 time steps to execute. So you do analyses of sequential versus parallel times on a target computer and see what it would look like. This is the actual Fsharp code. I'm not going to go into it. Anybody is interested, I can explain the lines, but that's how we generated the previous circuit. And this is it running. So this is 20 entangled qubits. Takes about 2 seconds. That's in the brackets each time. We get all zeros and all ones, as we'd expect. This is running on my cluster. So anywhere from 80 to 100% utilization. That took 1,000 runs of 22 entangled qubits in 3.5 minutes. So now we're starting to get into some more interesting scaling. Yeah.
Is this the universal?
Yeah, this is all universal. We're only talking universal at this point. So this, you can do anything in this one. Well, let's do something that everyone knows. Shor's algorithm. Let's factor. Okay, that's as soon as you say quantum, everybody says, oh, we're going to break RSA. And not so much. But this is a simple circuit. I should say the biggest number you see in any of the published papers factoring is the number 15. Okay, 4 bits. 4 qubits in this case. Actually, it's a 4-bit number, takes 8, 9, 10, 11 qubits to do. The circuit's actually 8,200 gates. One of the nice things about the circuit renderer is you can say, give me different levels. Like this is a more abstract level. I have modular multipliers here as units. I could say, go inside of those, show me the circuits, go inside of those. You can go at any level you like. But like I said, 4 bits, 8,200 gates, that's about what everyone's done. We've done 13 bits, which was the number 8189. It's about 500,000 gates. And the one running at home, I think I mentioned at the beginning, will go for 28 days. And he's doing a 14-bit number at the moment. Just to show you what the circuits look like, this is the modular adder. In the Fsharp code, I won't do it in detail, but there's a controlled add gate. So here's the problem. You want to add 2 numbers together, and you want to keep them from overflowing. It's a modular adder. Simple. Except the entire circuit has to be reversible. As I said earlier, everything has to be kept unitary. So here we do the controlled add. And we're actually doing this in Fourier space. So now that we've done the add, we have to bring it back out. We do an inverse, this is the inverse of the, no, it's not the QFT. This is an add, oh, I'm sorry. We're going to subtract off the number that we're modding to see if we overflowed or not. So we subtract the number off. Now we take it out of Fourier space. We do an inverse QFT, quantum Fourier transform, and we remember the top bit. If the top bit overflowed, we know we have to go back the other way, otherwise we don't. So we remember the bit in an ancilla, or the qubit in this case. Now we put it back in the QFT. Now we really do the add based on whether we would have overflowed if we had done the add. So this did the modular add. And now the whole rest of the circuit, we're going to do an inverse add, inverse QFT. We're going to clear that top qubit. We have to leave everything back the way we found it. So he's got to go back to being a 0. Now we QFT, now we add again, and now we're done. And you can run this circuit forward and backward, and everything is left in the right state, and everything works correctly. But this is why it's not as trivial as just say, take your classical algorithm and drop it into a quantum algorithm. By the way, we are working on that also. Someone else has a simulator they've written where you take a classical algorithm and say, make this reversible. Then take that reversible algorithm, make it quantum. So we're going to be adding that. That's higher level things we're adding to the simulator over time. OK, so what do we get when we do this? Here's an example of factoring all sorts of numbers, times they took. It's probably much easier to look on a graph. The blue diamonds are the first version of the simulator we wrote. Second version is the red, and the orange is as of 2 weeks ago. So we went from 3 years to 4 months to 4 days to do that 13-bit number. And as I said, the one that's factoring at home, the red line would be a month. It looks like it's going to be about 28 days to factor for the last one. And that's not anybody cares. That's, my dog can talk, not how well my dog can talk. But again, everything published to this date has been way down, all the way at the lowest on the left is the biggest anyone's done before this. So this just gives you an idea of the complexity of the full universal simulator, what you're able to do.
It also tells us something different, which is that the promise of factoring big numbers by using quantum computing, we could do it way faster than we could with an ordinary computer.
However,
Whereas here, factoring 8,000 could be done really fast, so that there's a really very enormous slowdown factor. So the promise is that quantum computers are going to be fantastically much faster.
Yes.
And here it's kind of like taking months to do something. Which
No, but this is doing a simulation of a simulation of a simulation. So the real quantum computer will do this blindingly fast. Okay, I'm doing all 500,000 gates and having to do them on a classical machine to simulate them. If I actually was doing this, I can do this on a quantum computer. That's actually not the I'm very fast. I can break RSA on a quantum computer. The problem is the number of qubits it takes, the number of gates it takes to fix up all the noise along the way to get there, and on and on and on. So when you actually...
The slowdown factor is kind of exponential inside.
Yeah. And so for some, and I'm going to show you places where it's not, where we actually do get an exponential win. But factoring works, but the actual technology you need to build the machine is a good 20, 30 years away before you could really build the machine to break RSA. And by then, RSA is bigger, or whatever you're going to use for cryptography. There is also quantum cryptography, by the way. You can really nicely entangle those qubits like we just showed you with Bob and Alice. And if anyone eavesdrops on it, you destroy it. So anybody trying to look at the channel will destroy the channel, so you can't get the information without somebody knowing, and then they can't get the key because the key was moved quantumly and on and on. So there's a whole quantum key cryptography area too. So let's talk about noise a little bit. I'm not going to go again into detail. I just want to give a feel. There's an abstract class you derive from, say, I have a quantum error correction code I want to try. This happens to be what's called the Steen 7 code. And this guy generates a circuit that says, given one logical qubit, replace it with 7 physical qubits. And this encodes the 7 into that code space. So I now have a nice encoded value that I can check for errors as we compute. This is the guy that actually does the checking. So the bottom 7 is the encoding of the logical qubit. The top 6 are the ones who read everything on the qubit, measure it out, and then decide to apply X and Z flips depending on what went wrong. And so this will actually fix all 1 qubit errors, will detect all 2 qubit errors. Sounds just like you do normal coding classically. But this keeps everything quantum. This lets you actually apply this throughout the system. And this is what our friend Teleport looks like once you run it through this quantum error correction application. It goes through and rewrites the circuit with all of those syndromes, and then every place you had an X gate, you now have 7 of them. Or the C naughts, or any of those other gates you saw, you now have 7 copies that happen at once, and then you check if we got what you expected. So yes, your number of gates blow up very quickly, and the number of qubits blow up very quickly. We also finished a brand new noise model that's much more physically accurate. What's nice is you can say specific gates have different noise models. You can say how many qubits they're going to operate on, how long in physical time the gate takes to work. A C naught, a 2-qubit gate, may take a lot longer than, in 20 to 50 nanoseconds instead of 10 nanoseconds for an X gate. And then you provide a noise model for what you want to use. So now for different types of qubits, different types of gates, even in the same system, they may be hybrid, you can apply your own noise models. The system gives you back events. This noise event happened at this time on this qubit, on this gate, and this is what it did. Also, your error correction circuitry is also going to be noisy. And that's a problem. It turns out if your gates aren't good enough above a threshold, the error correction makes it worse because you've added more gates, and the gates are noisy, and everything gets worse. So you actually wind up coming up with a threshold value of at what point do your physical gates have to be, how good are your qubits before you can even fix them. And so there's a whole interesting area. Krista Savory, who heads the research group, that's her expertise, that's her main area, is noise modeling and correction. But the one that's new that, again, nobody has, is we actually do non-unitary noise. We do what's called amplitude damping. So if you read in the papers, IBM now has a qubit that lasts 1 or 2 milliseconds. Sometimes you hear T1, their T1 time for decoherence. That's this. We can now model actual decoherence of the individual qubits as you're going. You can actually put different probabilities on different qubits. So you have semiconductor qubits, you have quantum dots, various other technologies you can put different decoherence in. So here's a simple circuit. Again, I've got a Hadamard, so I'm putting a superposition 2 qubits, and I'm C-naughting together, and then a bunch of idles, an infinite number of idles. What happens? Well, here's with the damping probability what happens. We start out with 25% probability for each of the 4 possible states, because you could read out the other end, 0, 0, 0, 1, 1, 0, 1, 1 when I measure it. But you'll notice everything with a 1 in it starts falling off, and the zeros start climbing. And then we get this non-unitary event. The thing just decohered. And so 2 of them dropped to 0. 2 of them popped up a little. Basically, the first qubit went to 0. So the 1, 0 and the 1, 1 state disappeared. And now you can see the 1, 0 keeps bleeding away to the environment as the 0, 0 keeps going up until he decoheres. And now everybody is 0, 0. You've lost your qubits. They're gone. So this is the first time that I know of anyone's actually built a simulator that will actually let you do the physical modeling of what's happening with the qubits. And for a sanity check, we took our friend Teleport, added quantum error correction on top of it, the Steen 7 code, put in some probabilities that were published by others for actual physical qubits, and we get a fall off at about 3e minus 3 where the whole thing can't keep up, the code can't keep up, and there's this threshold. And it turns out that's exactly what Steen predicted the threshold would be, right in that area for when you have physical qubits and they look like this. This is about where everything would stop working. So about 3e minus 3 has to be your T1 time for your qubits if you want to be able to correct them. If you can't keep them at least in this millisecond range, you're not going to be able to fix them. Yeah?
So are there some known physical kind of boundaries of how stable these qubits could ever get? I mean,
let me give you hope. The reason Microsoft is in this at all is we have an area we're working in, and our focus is called topological quantum computing. And I can talk to people separately about it. I wasn't going to do it in this talk, about Majoranas and these quasi-particles we're using. But it turns out, instead of having, say, a single electron that you're flipping the state on, you actually have a particle that 2 of them make up the electron, or the fermion, actually. And they're really one item, but they're separated in space. So these decoherence effects, if they hit one of them, they don't hurt the other one. You have to hit both at the same time, extremely unlikely. The times for these look like they could be in the years. You don't have the equivalent of computer memory, where these qubits can last virtually forever. It also means your error correction now became easy because they don't go away. You actually, the gates are done by braiding them around each other. So as long as you braid them and you don't get them near each other, you can actually do all of these gates and you have fully fault-tolerant computing. Now, there's lots of caveats. I'm going to leave all of that out for now. But the point is, this is why Microsoft is so interested. We have the only Fields medalist working in industry, Michael Friedman, who's down at Santa Barbara and at Station Q, and this is what we focus that whole effort around, is these topological qubits. Now, in semiconductor qubits and like, we're up into the milliseconds range. No reason it can't go higher. And that's enough. As soon as we get into the tens of milliseconds and a little beyond, we can correct them. We can keep them alive forever. So we're on the verge even for the more traditional or conventional qubits. So it looks pretty good.
And we cool them? I mean,
it's all done at superconducting levels. These are 20 millikelvin, most of this is run at. I can talk about fridges too. I got lots of pictures on my phone if people want to see. I've been going to all of our labs in Europe is why I'm here. And so we've got some very cool experiments going on. I'm just going to mention the stabilizers. These are the ones we can do tens of thousands of qubits. You can take your normal circuit, you compile it into stabilizers. This is Teleport, again, running in stabilizers. I'm not going to do any detail here. But for people who do this work, you can also get statistics out of where you are in the stabilizers and what the space looks like. But all of those error corrections we were looking at only were flipping X and Z, and it turns out stabilizers know how to do X and Z, and so you can do all your error correction. Let me do a little machine learning. Okay, PageRank. We're going to start with a standard stochastic probability matrix, the G matrix, or Google matrix, if you like. But we're going to turn it into a Hamiltonian. Take the identity minus G, adjoint it, and identity minus G. It turns out that gives you a Hamiltonian that represents those stochastic probabilities. Convert it to a unitary. This gets back to our Hamiltonian simulator we were talking about. So now, remember, the unitaries are gates. And we evolve it from a starting state of static probabilities, the 1 over n you would use for PageRank type thing. And then we do an adiabatic evolution. I won't describe the term unless somebody wants it at the moment, but there's a way to do these Hamiltonians and guarantee you can get to the lowest energy state. We accumulate the average probabilities. So here I do a synthetic web graph using recursive matrix generation, so it's a nice power law graph. 256 pages, by the way, takes 8 qubits, so I can do 2 billion pages in 32 qubits. I mean, it shows you very quickly. We can do big problems on tiny machines. And here you can see regular PageRank and quantum PageRank. We get the same answer. This is good. I can do extremely dense encoding, and I can pull PageRank off. There's a bunch of caveats. You'd never do this in real life. And I can tell you all of them, but let's just say it takes you exponentially long to actually get this answer out. It's there. It works, but you wouldn't do it this way. And the problem I have with a lot of the papers out there, everyone leaves the real costs out. And so what we've been doing a lot is, I'll use the word here, debunking a lot of this is exponentially faster. No, it isn't. This is quadratically faster. Well, only if you ask the question once and only want 1 bit of accuracy out. That type of thing. But don't worry, I'm going to end on a positive note. It's not all bad news. This is talking about the Hamiltonian simulator now. One of the most popular or useful techniques is called spin glass. So what you've got, think of Boltzmann machines, think of just standard simulated annealing. I have something that can flip up or flip down. I'm going to hook them together with strengths, positive and negative, and I say go, and everything flips around, and I lower the temperature until everything stabilizes out. Okay, standard technique. The way we label it here, or the way we do it here, the first term in the x direction basically is, think of it as your temperature. If I have that really strong, I'm turning off all the other links, or I'm overriding by saying push everybody in one direction. I'm going to make everybody go in the x direction. I'm going to lower the x direction and increase. The HIs are saying I'm going to clamp somebody up or down. So this would be like the inputs to your problem, right? You'd say these are my input ones that are a 1, 0, 1, 1, 0. And then the JIJs are connecting them with everybody else. You let this thing cool down, and all the others flip to an interesting state, and some of them you've defined as your outputs, and this is normal simulated annealing. It's known as a spin glass problem. There's a company in Canada called D-Wave who ships a quantum computer, back to the question of when we're going to see quantum computers, at least that's what they say. And we can reproduce on the simulator everything they've published in Nature and Science and all the rest. Give you an example using ferromagnetic chains. We turn this into a circuit. So what you're seeing is the first column are all the x's. Then I'm clamping the left and the right because it's a ferromagnetic chain. I'm going to say they're up, they're down, they're opposite. And then I'm going to link them together. Those are the JIJs. And finally, at the end, I've got the x's again because we're doing a higher order approximation back to the other question on trotterization. You can ask for higher order trotterizations and actually break the differential equation apart, be more efficient. And we get all the answers that everybody's published, and we can do noise modeling, entanglement entropy, all sorts of other things on here. If you're interested, this is going into Nature. It's being out for review right now, but they let us put this up. There's been so much buzz. They let us put it up on the archive, and there's a link there. If anybody wants to read it, there's a big, big paper on this and all the details. Traveling salesman. Here's an example of a Hamiltonian for traveling salesman. What you're doing is encoding the edges. So you're going to say, I want to drop down edges between cities. Oh, they are. I know. We've reached 11 o'clock, so it's OK. Oh, I'm getting to the end here. And anyone who wants to leak out, feel free. It's OK. I just want to mention the same problem with doing this classically is if you just naively put in traveling salesman, you start getting problems where you get disconnected roots instead of the full because there's no higher order constraints. We can do 8 cities, 28 qubits. Other people publish papers saying, oh, a higher order constraint lets me do more, like a 4-body instead of a 2-body simulation. Yeah, I get a doubling in the speed this solves that, but it's 4 times the amount of work. And that's the part that gets left out of the papers. Yeah?
Can you comment, what's the result for quantum computation for NP-complete problems?
In terms of what the result?
It's not supposed to work in polynomial time, right?
No, never said that. All I'm trying to do is reduce the prefactor. Okay? I never made a claim that, P equals NP or BQP is P or any of that. No. Okay, I'll finish fast. Unfortunately, this is probably the best part of it, but we'll just leave it. I took too much time on the other. There's another Hamiltonian model, second quantization. This lets you do molecular chemistry. This is H2. two hydrogens together. This is simulating it. The blue is our simulator. Compared to published results, we actually get more accurate results. We're actually telling you naturally where the two nuclei will come together to balance out the energy. You can run the whole thing from script mode. You can run this on a cluster. This is all of water being simulated. So this actually is doing bond lengths and angles to show you what a water molecule. We're back to what Feynman said you'd use a quantum computer for, is simulating quantum physics. Again, we get different numbers in the traditional approaches, but when you solve it exactly, what we get is exactly the right answer to the precision we asked for. The problem here, this takes 34,000 gates. Then you got to run it 2 to the 14th times to get 14 bits of accuracy, then another 2 to the 10th time to get rid of the commutativity problems, and then about 50 samples per point to make sure you got the ground state, and 546 points for the plot. This is 10 to the 16th gate ops. We can cheat. And so we do what the quantum chemists do. I'm not going to go into this now. Everyone interested, this is a linear algebra you can do to get your 2 to the 15th by 2 to the 15th matrix down to 441 by 441. Oh, and once you've done that, your exponential powers of 2 just become matrix multiplies times themselves. And that's how I solve this, actually. Okay, I can't actually run the gates for the length of time it would take. These are all the raw numbers for if you now add, oh, I don't have all the rotations. Oh, I have errors. This gets very big. And in fact, there's an IARPA challenge using a molecule called ferredoxin, which takes about 10 to the 23rd gate operations. That's a century and a half at current technology speeds, back to when will we have this. However, we've come up with a new technique that will let you take the scaling down from n to the 4th, where n is the number of orbitals of the molecule, down to n squared, with no reduction in error. And in fact, if you're interested, this isn't out yet, but there's a paper coming that if you notice at the bottom, there's a 5.8 billion gate operations needed for ferredoxin. We've got it down to 37,000, which took your century and a half down to a week and a half. Now it's reasonable. And that's with today's qubit technology in terms of speeds. So we've now reached a point where we can do, you build a machine that can do this, you can do much further than chemists can do today. They can get to maybe 100 orbitals if they're lucky. We can get to hundreds above that and solve very complex molecular problems. I'm going to give you one more example that I'm also working on right now with Matthias. You can also do simpler Hamiltonians. You can do effective models. And when you do that, this is called the Hubbard model. This scales linearly with the size of the problem. So I can actually simulate entire sheets of superconductors and design high-temperature superconductors this way. So in fact, on the right is from a paper he previously published. On the left is liquid simulation of the material. These are cuprates, which are high-temperature superconductors. And by the way, the numbers aren't the same because, again, we went, built it, did the simulation, and found their numbers were wrong. So in lots of cases here, when you actually implement it, I'll give you one example, Shor's algorithm. When we implemented it, we found the paper was completely wrong. They left a gate out that all you get is random answers. You don't actually get the real solution. And no one ever knew it because no one ever simulated it. And there's lots of documentation. I can give anyone who wants this paper. We're actually going to put it up externally, which is just an overview of what this talk talks about. It's also an 80-page user's manual. There's MSDN documentation. And that's probably enough for today. So I'm here for 2 days. Anybody wants to talk, my schedule right now is wide open. And I'm at your disposal.
Thank you, Dave.
Questions? Sure.
So going back to Benjamin's remark, and you were saying you need to keep track of the whole space. Is there no theory around getting insight from what you're going to query in the end and get some variational bounds or something?
The problem is you're entangled. As soon as you have entanglement, you can't even look at the state. One of the things we didn't talk about in here at all is debugging. How do you figure out where you are in all of this? Even before you can do it variation analysis, I even have to understand the system. And I can't. And there are a bunch of techniques we've started putting quantum debuggers together. But you can't like single step and ask what are the values of the variables because it's distributed across 2 to the 30th elements. What do you do? Well, it turns out there are ways you can make believe you measure. We can do things you're not allowed to do quantumly. But that's a whole separate we can talk about. But it's really, it's terrible. You can't, by the way, you also can't clone. These are linear types, if you prefer. Once you've read it, you can't read it again. And it's gone from where you read it. So you can't copy anything. You can't look at it without destroying it, on and on and on and on. Now, again, we're simulating, which means we can cheat. So the things we can do, you copy the whole state vector and do stuff to it that's illegal and then keep the rest of it going. Okay. But even so, the analysis is such that, I said if they weren't entangled, I could bring this thing down. I don't know when things aren't entangled. You have to tell me as a user, I've just separated these. The circuit did the right thing. They're now disentangled. Yeah. But you can say, check that I'm right, which is extremely expensive. And it goes through and figures it out and lets you know if it is, then it really disentangles it. Otherwise, it says you have a circuit bug, that type of thing. So we do have all of that implemented, but automatically in any efficiency being able to do that is virtually impossible. Frustrating. It's fun, but it's frustrating. Yeah.
For the results that you talked about at the end of your talk on molecular simulations, how much of that is done using your current simulation, and how much of it is waiting for actual quantum computers?
Oh, all of it's the current simulator. All of it. Now, let me caveat. Everything through water, H2O I can fit in under 30 qubits. The others I can compile the circuits and get all the numbers in those tables are from the simulator, but I can't run them. Right? But we verified the techniques we're doing, this multi-resolution trotterization, that we can actually throw away 98% of the matrix. This is, again, it's basically doing a multi-resolution decimation of the matrix. So we precondition the matrix and figure out what doesn't matter and throw them away below the accuracy you care about. And by doing that, these are a lot of it's standard linear algebra techniques or HPC techniques that have never been applied in this field. So, but in answer to your question, everything you saw up there of H2, H2O, those have all been fully simulated. And actually, water only takes about a minute for me to do once I've done all of those classical tricks. On a quantum computer, it would take longer, actually, because I have to do all the gates. Sure.
Yeah, so I didn't quite get the transition from the gates formalism to the Hamiltonian one. Can you explain that connection again?
A gate is a summary of a time step of a Hamiltonian. So e to the I ht is the unitary. So over a period of time, when you run those gates, they go to a steady state. So the x, the y, the z, the Hadamard C naught are all steady state solutions to applying the Hamiltonian. So the Hamiltonian is the transition to get from one to the other. And normally that's fine. If I'm doing digital operations, then I'm fine. I'm saying I want to flip this bit. Well, I have to move it. I have to actually move the qubit and flip it. And that's the Hamiltonian. Doing that, the unitary is the effect of that. As Simon was saying, that the whole point is, why can't I just do that? Well, the problem is if I'm doing spin glasses and things, they're all flipping, and while they're partially moving, they're talking to each other. And so now I actually have to go down into the Hamiltonian and actually do traveling salesman or whatever the machine learning type problem I'm mapping onto it. PageRank is like that, for example.
That's like solving the Schrödinger equation.
You are solving the Schrödinger equation. Yeah. The Hamiltonian does a full Schrödinger wave equation, basically. Yeah. Okay, well, like I said, I'm available. Thanks.
Come and see Dave. Make time to see him. Thanks.